is this one of our purple sheet integrals? Because if it is, then this is easy, right? Do we have any integrals that are 1 over square root of something? Let's check. Oh, so close. We have that sine inverse is 1 over 1 minus. Unfortunately, this is 1 over 4 minus. But we could do a substitution to make that work. And there's two ways we can make that work. If we're thinking of a 1 minus, so in our heads we have, I know this is one of the ones that I know, but that's sine inverse. There's a couple of ways we can do an algebraic manipulation to make that match up. Method 1 is you just think of a substitution. However, I feel that thinking of the substitution is actually easier if I want this 1 and there is a 4, why don't I factor out a 4? And if I factor out that 4, there's a multiplication here. Well, this is really square root of 4 times square root of this. I would really have a 2 out in front. And this is 1 minus. And again, this formula works when it's 1 minus something squared. So I have 1/4 x squared. Instead of writing it that way, I put it in brackets as 1/2 x. Yes, I know. It looks like scribble, scribble, scribble. I will. Does that look better? Maybe don't answer. I could change 1/4 x squared to 1/2. Still don't like how it looks. 2, there we go. This. The 4 comes out as front as 2, leaving you with 1 minus, and instead of 1/4 x squared, I want to write that as one thing squared, and I'll change that then to 1/2 x. Because 1/2 x times 1/2 x would be 1/4 x squared. And now I have basically this idea, 1 minus something squared, with an extra 2 out in front. If you really want it to match, you can do a substitution now. I can change my u to 1/2 x. I can find my derivative, which is just 1/2. And when I substitute, it matches up perfectly. Right? The 2 on the bottom is part of that 1/2 dx, gets substituted out. And its integral is sine inverse of u plus c. So now I can substitute back, and I have sine inverse of 1/2 x plus c. So in the algebraic manipulation ones, you look at the integral, and it looks close to an integral that you already know, just with numbers mixed up. So if you look at the next example, which one on your purple sheet does it look close to? Are we ready? I can switch here? We're good? Okay. What does it look close to? Right, do we have any with an x squared on the bottom? Yeah, tan inverse, right? Tan inverse has 1 plus x squared. So mathematically, I have a 9 plus. I can factor out that 9. If I factor out that 9, now I have 4/9 x squared. I can rewrite that 4/9 x squared as a 2/3 x, all being squared. Okay? Things match up nicely, and I can substitute in the u for the 2/3, which, solving for the dx, becomes 3/2 du. So the numbers didn't match up nicely like they did last time. Last time the 1/2 matched up perfectly, and the substitution was clean. This time, it doesn't match up perfectly, but once we substitute in, so I put in the u for the 2/3 x, the 9, I could just have that out in front. I have the 3/2. I could pull that 3/2 out in front, which just becomes a 1/6. And then that's just tan inverse of u. Substitute back. I forgot the plus c. So this has a mix of substitution and algebraic manipulation together. Yeah. So, you see the square root of 1 minus x squared on the bottom. That matches up nicely with, well, there's a couple of them, with both the sine inverse and the cos inverse. But generally, whatever's on the back of this purple page that I gave you, you kind of can ignore it because they're covered on the front, right? So I would think sine inverse. But the problem is on the top I have 1 minus x. And it can take you a long time to see this, but if you unadd fractions, have you ever thought of the unadding fractions? That this could have looked like this before you added it together. It would have been this minus this. That's breaking apart a fraction that was put together. All of those years where they taught you how to add fractions and now it's sort of like someone went too far. They made it harder on you by adding them together. If we split them up, well, because of the properties of integrals, you can just integrate them both separately. And you can put that you could have a subtract sign if you wanted instead of an adding sign, or you could put that negative inside. That really doesn't matter. But what's crazy here is that the first one matches up perfectly with sine inverse now, right? And the second one is a beautiful substitution one. It's no longer sine inverse, but you see that the 1 minus x squared, I can make that my u. Then the du would have an x. We'd have to manipulate it a little bit. And so the first one, perfectly sine inverse of x. The second one, well, once I do that substitution of u, I can integrate that as well. Now, technically, when you integrate the first one, you'd have a plus c. When you integrate the second one, you'd have a different plus c. And if you put two different plus c's together, you would get a different plus c. they're not really worried about notation. You can just have a plus C all the way through on this. No problem. And we can substitute back in the end. And we get a very unintuitive answer. But if you wanted to, you could take the derivative, add the fractions together, and you would get the result that we have. Partially what makes integration so difficult. Derivatives is easy, because you're going in one direction with the same rules every time. And then once you've gone in that one direction, you're like, oh, I have like terms, or I can put things together. And you put things together. And then when you want to work backwards with something that's put together, it's like, oh, how should I break this apart so that it works out nicely? So the unadding of fractions comes up a fair bit. We have it. Can I show you the last example? How do you recognize the unadding of fractions? Well, usually the unadding of fractions, one of them has a 1. Because almost all of your inverse ones have 1 over something. So this one, I look at it and say, I could break it up as 2x plus 1. The first one, when I want to integrate, that's going to be a substitution, because the bottom's derivative is the top. The second one almost looks like tan, but I'm going to have to do some playing around and do a different substitution for that one. So it's sort of like 2 hard questions put together in one with a little trick to get it to the 2 hard questions. Wonderful. And I'll put up the answer.